Welcome to the second episode of Zeroing In, the Science Podcast. This is Shreya Mishra, and joining me today is Prajwal Patnaik, who recently graduated from the Indian Institute of Space Science and Technology, Trivandrum, with bachelor's in avionics and is currently pursuing his master's in business analytics at the University of Technology, Sydney. Our guest for today is an academician, an innovator, an eminent researcher, an administrator, and a music enthusiast who has dedicated his life to pursuit of excellence and in enabling countless bright minds to do so as well. He received his bachelor's degree in electrical engineering from Jivaji University, Gwalior, and then went on to pursue his master's from the Indian Institute of Technology, Kanpur. His doctoral work in astronomical image restoration took him for the first time to IIT Bombay. His career trajectory is rich and vivid in experiences, with his longest spell at IIT Bombay, where he served as a professor in the Department of Electrical Engineering for more than 20 years. He has served at crucial administrative positions at IIT Bombay over the years, is the former director of IIT Delhi, former Vice-Chancellor of University of Pune and Bennett University. He currently holds the position of Professor Emeritus at IIT Bombay. Notably, he pioneered the digital education activity in India with his extensive contribution to the National Project on Technology Enhanced Learning, or better known as NPTEL, which is now recognized as an indispensable online learning resource in the country. In our conversation with him, we discovered about his journey, his ideas about the field of radio astronomy, fiber optics communication, and computational electromagnetics, to which he has made seminal contributions. We also talked about the evolving technologies that have implicit as well as explicit implications on the lives of our community as a whole. A very warm welcome to Dr. Raghunath Kashinath Shevgaonkar. Sir, we'd like to begin the conversation with a brief discussion about how you came into the field of science and where did your initial interests lie and how did it all begin basically, and how were you like as a student in school and in graduate school?
So science looked exciting at that point of time. The mathematics I always enjoyed, especially when first time when I was exposed to calculus. I was really thrilled by that. I mean, the concept of limit, that itself was so exciting that something, when you look in terms of limits, things look completely different. So when the derivative was defined and I just went through that first step of calculus, I was completely zapped by calculus. So you'll not believe it, but even when I was in my high school and when the calculus was introduced, before even the school started, I completed the entire mathematics book in my summer vacation before that, because I really liked it. So that was something which was there. Science was always very exciting because one of my teachers who used to be there in my school, who used to explain many of the things by practical demonstrations, like focusing of sun rays and burning the papers, and many other things, which look very exciting at that point of time. So it looked that scientific way of thinking and doing something with science is very exciting. So that's how actually my schooling was. I got some good teachers who could excite you in science and good exposure in mathematics, and which I really enjoyed.
So, sir, can you also talk about how your interests inclined towards the core field of electromagnetism, and why was it that you decided to move into research?
Yeah, so I had no great intention of going into research. It is just I wanted to get a little higher qualification, which will build my job prospects better than anybody else. So that was only the motivation at that point of time. However, after I went to IIT Kanpur and the kind of academics I was exposed to, then I started really seeing how good, how beautiful the academics could be. The kind of courses which were taught in IIT Kanpur, they were at such a level and such a inspiring experience which I had, that I really fell in love with some of the subjects. And one of the subjects was, of course, the electromagnetics, for which I was specializing in IIT Kanpur. And that time, that subject used to be almost the topmost subject for choice.
Hmm.
So the toppers used to go for the electromagnetics, and then of course communication and VLSI and many other subjects were there. But the electromagnetics was always at the top. So that's the experience which really motivated me to get in more deeper into the subjects of science. Of course, I always had some liking for physics, though I got into electrical engineering, but I always wanted to do something in physics. That always looked much more interesting, than normal application kind of courses. So that was my beginning actually in science.
So I'd like to ask, from the time you started working, how did your research directions evolve based on the daily lives of people? For example, talking about antennas. Right now, we are carrying antennas literally with us everywhere in our mobile phones, and it's an indispensable part of us. So, how did you see the correspondence between the two, the research direction that you were pursuing at the time, and how things were evolving?
So when I was doing my MTech in IIT Kanpur, as I mentioned, I always enjoyed the subject of electromagnetics. And I did my MTech thesis also, which was on propagation of light in the anisotropic optical fibers. And that time, which was like mid 70s, the optical fibers were just coming in. So even if you could launch light inside the optical fiber, that will probably become a BTech project. It was at that time, and people were doing more theoretical work in understanding how the light would propagate inside an optical fiber. If you wanted to send the information by using light or optical fiber, what are the issues which will be there, like signal distortion, the bandwidth issues, the distances over which the signal can be sent. All these things actually were at the primitive stages. So I did my MTech project, which was on propagation of light in anisotropic optical fiber, and I could publish probably one or two papers also through that, from my MTech project. So that gave me some confidence that I can do some independent work, and which is not published already, which is not done, and that is the right direction for doing something like what is called research. But getting into astronomy, which was my major field of research for almost a decade, that I got almost by accident. So as I said, since I liked electromagnetics and I could relate it more to the antennas, since my liking was always electromagnetics, and antenna was one of the subjects which was more practical oriented subject in electromagnetics, other than the propagation of light and electromagnetic waves. Another thing was that the professor who used to teach the course on antenna, Professor N.C. Mathur, his style of teaching was so excellent that you will really fall in love with the subject. And that's how it happened. I fell in the love of the subject of antenna. Then it so happened that that time, Indian Institute of Astrophysics and Raman Research Institute, they were building a telescope, Gauribidanur, near Bangalore. And they were looking for an antenna engineer to design and erect their large antenna array. When I went there and I saw the whole system, I really got thrilled because that was an antenna which I had seen first time in my life, and that antenna was 1.5 kilometers size, a 1,000 dipole array. So it looked so exciting that I almost instantaneously I decided that I would like to work with this instrument. I would like to build this instrument, and I just got into that as electronics engineer. Later on, of course, the life took a different turn. I became a astrophysicist, for a decade. But that was almost like nothing was decided a priori. It just the way the things came. I just went on sort of accepting it and making sure that I always do something quality work, which actually put me into this research area.
Here, I'd like to ask a very basic question, which might come as a genuine doubt to a lot of people. Can you briefly explain how exactly an antenna works? Because a lot of us don't know about it, and because it has remarkable importance in all fields. For example, like I said, in our everyday lives to advanced military applications as well.
Right. So the principle of antenna is basically the fundamental nature of the electron or charge for that matter. So if you have a charge, then the charge gives you the electric field. We all know that, right? If the charge is put in motion, then it becomes a current, and then it produces the magnetic field. So if you are having a charge which is moving with constant speed, which is just a DC current, then it gives you magnetic field. That also we know. Question is when the charge is accelerated, then what happens? That is the origin of the antenna. So when the charge is accelerated, then it produces an electric and magnetic field both, and then it throws the energy out, which is supplied to the charge for acceleration. It doesn't keep the energy with itself. So any charge which is accelerated, and acceleration of charge means any current which is alternating current. Any time varying current will always have acceleration of charges. So in principle, any accelerating charge or any time varying current will produce radiation. It will produce electric and magnetic field both, and then one can show theoretically that you can have the coupling of these two will always give a phenomena what is called electromagnetic wave, which will carry power with it, and this power will just detach from the charge and will start traveling into the space. That's what actually happens. So in principle, if you ask, any alternating current should be, and need not be sinusoidally alternating, any time varying current in principle should give you radiation. Question is how efficiently you get that radiation. That's what the antenna is. So everything will radiate. Can you efficiently transfer the power from a guided system, what is called circuit, to the space in the form of electromagnetic wave? So that is the way of looking at how the antenna actually functions. So though in principle any time varying current will radiate and will give you radiation, antenna is a more efficient structure which will efficiently take the electrical power and put into the electromagnetic waves in space. Right? That is basically the antenna.
Thanks a lot, sir, for explaining it so fundamentally that I think anyone, even from the outside the field, can understand this idea. Most of us imagine antennas as the dish antennas we used to have on our rooftops for dish TV and all. But now to think antennas have, shrunk down to chip sizes so that we can carry it on. How did that happen? I mean, what is the basic structural design? How it changed from that to this? What was the technology advancement that took place in between?
No, so actually the efficient antenna, if you really consider, any body which has a dimension comparable to the wavelength, okay, can give you radiation reasonably efficiently. So for example, you take a piece of wire, and if the length of the wire is equal to half the wavelength at which the energy is supplied to it, it will start radiating what is called a dipole antenna. So antennas which you are seeing in your mobile phones and so on, there are two things have happened. One is the frequency of operation has gone much higher. For example, if you go to your broadcasting station, the normal AM or FM station, what are the frequencies you use? The AM you use the frequency of few megahertz, few 100 kilohertz. For that, the wavelength is of the order of about few kilometers, right? So there you use an antenna which is like a dipole antenna or a monopole antenna, which is only a fraction of that wavelength. As you go to higher wavelength like microwave, the wavelength has become almost now 10 centimeters or 15 centimeters. So the half wavelength of that is only about 7 centimeters. So you can now, if you look at, if you wanted to make a half wavelength dipole, only few centimeter size is enough to give efficient radiation. So why the antennas have now become smaller and smaller? Because your wavelength operation has become larger. So without even going for parabolic reflector, which gives you much higher gain and focusing capability, if I don't want to focus the energy too much in a given direction, right? And that's what we require for mobile communication. Mobile communication, we don't want to focus energy in a given direction. Signal may come from any direction, right? Or similarly, anybody can receive signal from any direction. So energy, what we want to put into the space, ideally should go in all possible directions. Yeah. If I put a parabolic dish there, energy will get focused into a particular direction, which I don't want. I want that also, but that may happen only for the cases like microwave link, where the two antennas have to look into each other, just one line of sight, one point to another. But if I wanted to have a normal mobile communication environment, I would like to send the energy in all directions. And that can be achieved very easily by using dipole or monopole antennas, which are not very directional. So if I go to your handset or something and put a simple printed antennas, they have the what is called beam width of the antenna, which is much wider, and energy can be sent in very wide angle direction so that large number of people can receive it. So that's what has happened into the antennas. The frequency is increased, and that's why the size has come down.
It's quite interesting to know the details you put very lucidly, such that we get an extensive picture in our head. So, moving to a little personal side, why did you choose astronomy and how did it come together for you? And what were your major learnings, academic or otherwise, as well, from your doctoral work project?
Yeah, so as I mentioned, radio astronomy was not really by design. I went and joined this project in Raman Research Institute and the Indian Institute of Astrophysics as an antenna engineer. And I built this array, which is 1000 element array, which is what is called phased array. After this telescope was ready, I had two choices. One choice was to become a maintenance engineer and stay there for the rest of my life. Second choice was start using the instrument and start doing astronomy yourself rather than giving the instrument to somebody else to use it. And you become yourself an astrophysicist, try to understand astronomy. I thought second option was much more interesting. So I started learning astronomy. I did some courses in astronomy. And then I started doing astrophysics. So I started observing. That's how I got into the astronomy as a subject. Second experience which I had in this Gauribidanur telescope was there are very few people who were there who were working on the telescope. And there was no work defined for anybody that you are an antenna engineer, so you will do only antenna, somebody will do electronics, somebody will do image processing. Every work is everybody's work. And that was something which was very nice. So if the dipole is broken, you yourself go to the field and solder it. If the electronic circuit fails, you open the box and take out the chips and put yourself the chips and design and do yourself. So, so when we went through all that thing, you had a very wide hands-on experience on every aspect of a radio telescope. You could talk about antenna, you could talk about electronics, data acquisition, the image formation. You can talk about image restoration, and then you can do the science on with that. You can understand the physics, what is coming out of that. So that was very exciting because you are not defined any boundary for yourself. Anything, whatever comes to you, looks exciting. It looks great. You start doing it. You know? And then it so happened that again, when I was working there was one professor. He came from University of Maryland. He wanted somebody who can work on radio astronomy, image related problems. So I went to United States to University of Maryland and started working with very large array, which is that time one of the largest telescope. But this professor used to work on solar astronomy. He used to observe sun at radio frequency. And that time it was quite new because sun was always seen at optical frequency. How sun looks at radio frequency, how different it could be at radio frequency. I started working on that. And that's how actually I got more and more deeper into the physics of the cosmic bodies. Sun is a very rich plasma laboratory. Anything you can do in plasma physics and you cannot do on Earth. Everything is happening on the sun. Only thing you would observe it, understand it, and see what is really going on. So basically, when you do this kind of thing, observation with the VLA, exposure to the solar astronomy, which is a very rich source of information in plasma physics, your base really widens. So you are no more an engineer now. You are no more an antenna engineer. Right? You have become astrophysicist. You have become solar physicist. And that's how actually I expanded my research area. And at every stage, everything looked very exciting.
It was very interesting to know your take in a very non-scientific way. You put bounded input, bounded output, and multi-input, multi-output. Like you said, never bound yourself. You didn't want to bound yourself into one thing so that you will get bounded output.
Yes, here I'd like to talk further about the Gauribidanur telescope, which you already mentioned earlier. Can you tell us about the significance of this particular telescope and how has it contributed to India's astronomical research at the time?
Sure. So radio astronomy, when you look at the radio astronomy or the radio spectrum, if you look at the radio spectrum is very, very wide. Right? When you look at optical spectrum, the lowest frequency of optical visible spectrum to the highest frequency of visible spectrum. What is the ratio of the frequencies? Almost factor of 2. About 4,000 angstrom to 7,000 angstrom. Almost factor of 2. Right? If I go to radio frequency, the radio spectrum ranges from 10 megahertz, which is 10 to the power 7, to 10 to the power 11, which is 4 orders of magnitude. a very, very wide spectrum at which you can observe the universe. Question is, why should I observe universe at different frequencies? And if I observe universe at different frequencies, would it be different? You can see that when I look at a particular body, why do I see that body? I see that body because that body is radiating. That body is sending you some radiation which reaches to you, and that's what gives you the sense that there is a body there. Normally, when we look at a body, we see the body because of the temperature of the body, right? What is called thermal radiation.
Yeah.
So if there is a certain temperature of the body, the black body radiation spectrum says this body will have the maximum radiation at certain wavelength. If I look at sun, the sun's temperature is 6000 degrees Kelvin. 6000 degrees Kelvin, if I go to black body, it will radiate into almost yellow color maximum. That's why sun looks yellow, because its temperature is 6000 degrees. Right? Suppose the body was at a temperature which is higher or lower than this. It will not be seen and visible, but it will still radiate. Yeah. Right? So even if I look at black body radiation is not one frequency. It is a spectrum. Maximum radiation is at particular frequency, but on below that also it radiates, above also that radiates. So a radio frequency also, when I go, I see the thermal radiation. The body will radiate. That is one mechanism. Other mechanism which is also there happens in universe is that you have these electrons which are there in magnetic field which is there in the universe. And these electrons are accelerated by various means. And when these electrons go and gyrate around the magnetic field, then these electrons start radiating. Okay. So you know the phenomena, what is called gyration, right? Cyclotron phenomena. So you have a magnetic field, you have electron, and the electron starts spiraling around it. When it spirals around it, it accelerates. And we have seen that when the charge accelerates, it radiates. Right? So that means this will give radiation. So this radiation, because of cyclotron frequency, you see the radiation at its cyclotron frequency and its harmonics. Right? So depending upon how fast the electron is rotating and what is the magnetic field strength, the electron may radiate at 1 megahertz and double of that, and 3 times of that, and 4 times, and so on. Suppose the electron is accelerated to a very high speed to make it relativistic, then you will see that the same cyclotron phenomena becomes a synchrotron phenomenon. Right? So then the frequency, the radiation doesn't come at discrete frequencies. It comes almost as a continuum. So any frequency which you go, you will see a radiation. Now the difference is, if I look at a black body radiation, the black body radiation has a higher radiation coming at higher frequency. And as I go to low frequencies, the black body radiation becomes less and less. When I go to synchrotron radiation, the synchrotron radiation is exactly opposite. It becomes stronger at low frequencies and weaker at high frequencies. That's what synchrotron radiation is. So those objects which are not radiating because of its temperature but because of the synchrotron mechanism will become more and more visible at low frequency. And that's why radio astronomy is important, because these objects were never seen in optical astronomy at all, because they are not radiating because of temperature. And by the time you reach to the frequency of optical frequency, their intensity has died down to a very low value. But these are very strong radiators at radio frequency. One of the example is your own galaxy. These are the ones which radiate at very strongly low frequency. That's why people wanted to see the objects which are otherwise invisible by going to the lower and lower frequency. Gauribidanur telescope came at a frequency of 34.5 megahertz, which is almost the lower end spectrum which you can see from Earth. Why the lower end spectrum? Because below 10 megahertz, the ionosphere cuts away the frequency. Energy cannot propagate. So below 10 megahertz, if you want to see from the Earth, the sky is opaque. You will not be able to see it. You have some residual effect, so little away you have to go from that. So about 30 megahertz, 35 megahertz, that frequency becomes where ionosphere is reasonably transparent for radio frequencies. but low frequency enough to see the synchrotron radiation which is coming from the object. That's where these frequencies are chosen. So that time when this telescope was built, there were only few telescopes working at low frequency. There was one which was in US, what is called Clarkley, and another telescope which was there, which was Gauribidanur. So very few telescopes that time in the world, and I must say that in radio astronomy, the India was almost at par with the global standards. Not only in Gauribidanur, then the Ooty radio telescope came, and many other, now GMRT is there. We always worked, Indian scientists always worked at a level which was no inferior to the global standards at that point of time. And Gauribidanur telescope also was one of the state-of-art telescope which was working at low frequency. That was the importance of the telescope.
Sir, here we'd like to take a small detour, and I'd like to ask you a question about your career trajectories, which have been extremely lush and quite indulging, to be honest. I mean, you've closely worked with research and then industry and then academia as well. So basically here in all these aspects, there are various expectations which are extremely different when you of seeing a problem, how you look at a problem, and even prioritizing the tasks under the belt. So how did it all come together for you, and did you plan on all of these things, and how did it take forward?
I always tell to the students, and I think take this as a message: think like a scientist, but deliver like an engineer. If you look at engineer job is to develop something which works, even if you don't understand it fully. If it works, an engineer is happy, right? But if something works, but if you don't understand it fully, it's not a good situation, no? So we want something which you should understand also thoroughly. It should work also, in fact. That's what I'm saying. So you should think like a scientist to understand. Don't take anything for granted, and then produce something which works in real life, which is an engineering approach. So radio astronomy actually gave me this good combination. I could think like a physicist. I could build the instrument which should work finally, and that was something which was a more holistic development, which as an engineer or a simply scientist probably I would not have got. So I give full credit to radio astronomy for this, which is a science, which is a experimental science, and where everybody does practically every possible thing related to that field. Nobody compartmentalizes himself in radio astronomy. So that is something which sort of defined my trajectory, right? So any problem which comes in engineering, for example, you never ask a question, does the solution exist? You have to make it exist, because this is an engineering problem. We want a solution to this. Right? Right. So that's how actually you start doing the work. Problems keep coming. If your approach attitude is that no, I have to find a solution to this, and then this does not remain confined to only science. It does not remain confined to only engineering. It becomes part of your life. It becomes part of your professional career. So even if a problem comes at an administrative level, you have to find a solution. Find a solution. So if you put that attitude, naturally people will start dragging you more and more into administrative side. Any problem comes in functioning, they will ask you, you come and solve it. You get more and more involved. That's how I got slowly into administration also. So I became hostel warden. Then they found that maybe I'm more suited for being a dean of student affairs. I can interact well with the students. When I did that, then they found maybe I'm suitable to become deputy director also. So that's how you get into it. But if you put a positive mindset that no problem is unsolvable, and no problem is somebody else's problem, it is your problem. You become institutional person, and then you get more and more involved into your administration. So of course you have to strike a balance between your academics, your research, and your administration. You should not be carried away only in one direction. Right? So that is only the art of the game. How would you balance the thing. But if you could do that, then it is quite enjoyable.
Over the years, how has your understanding been changing? I mean, like even now, of the world around and of the work you have pursued. And as you mentioned already, that it's a wide span of the fields that you worked in, and in such varied fields that we cannot even account properly for. So, what were the major learnings and that you understood, or how did it all evolve of the idea of looking at the problems that you did?
See, one thing, that whatever you do, you should enjoy it. My philosophy is also a little different. You should not do what you enjoy. You enjoy what you do. Okay. Many times you are supposed to do something which you never wanted, but you have to do it. But if you are doing it, you as well do with great happiness. The results will be much better. So when first time when I did from IIT Kanpur, I went to Gauribidanur. Somebody asked me, "Do you want to do astronomy?" I said, "No, I'm not interested." But when it came, you start doing it, but do with happiness. And when you start doing happiness, you really start seeing happiness in that. Everything has a lot of interesting things which are there. So start getting the things done with happiness, and without saying that no, I will not do this or I will not do that. I think it makes the life much more enjoyable. So when I went to Gauribidanur, I started doing that astronomy. After that, when I came and joined IIT Bombay, there was no radio astronomy in IIT Bombay. Okay, but the students were interested in image processing and optical fibers. So I said, okay, so let me modify myself and change to this direction which the students want. So I started working in more image processing. Image processing background I had from radio image restoration. But then the other images which are there in which the engineering fields are interested in is not astronomical image. They are more interested in TV images or videos and their compression and their rectification and many other things which are there. So I started guiding students into that direction. At the same time, the optical fiber communication was coming a big way. This I am talking about late 80s. So that area which seemed to be a very hot area. So I started doing optical communication. At that time, optical communication has already crossed the phase of the primitiveness. Communication was already set up. It was functional. People were communicating by using optical fiber. And in fact, lot of information and power was getting put into the optical fiber. And interestingly, the medium, the kind of power which was put into that core of the fiber, which is only few micron diameter, the intensity of light inside the fiber was getting so high that the medium itself was changing its properties because of the presence of light. What is called the non-linear effects of optical fiber. So the material property depend upon the signal, and the signal properties depend upon the medium. Entangled problem, right? That looked to be more interesting problem. The non-linear propagation of light inside the optical fiber. So I started looking into working in that direction. Some students work in nonlinear propagation of light in optical fiber, and that's how the direction got changed. Then many new ideas came in optical communication, and I sort of keep on guiding myself to what are the new things which are coming in that field. So it sort of happened naturally. You don't decide that I will going to do tomorrow on this or that. New fields start emerging. You keep on adapting yourself to that, and you'll find something always exciting.
Okay, so talking about the disciplines of photonics and fiber optics, given how fast the field is evolving and how extremely application based it can get, how do you look at the future of the field in the national as well as the global scenario?
Yeah, so as I said, optical communication definitely is going to remain the backbone of your communication system, because today there is no medium which is as low loss as optical fiber and has as large a bandwidth as optical fiber. Right? So now the techniques are actually to how to really get more and more bandwidth. Whatever bandwidth you have got from optical fiber, single optical fiber bandwidth is almost 10 to the power 11 hertz. Okay, one TV channel requires how much? 4 megahertz or something like that. So about 4 into 10 to the power 6. One single optical fiber has a capacity of 10 to the power 11. That means about 1 lakh TV channels can be transmitted simultaneously by using one optical fiber. But today, when every house is getting connected, right, so much of video data is flowing, even that bandwidth is not enough. So you require multiple optical fibers, right? So again, maybe one is using optical fiber, but you can use different modulation techniques now. So essentially now the research is in the optical domain itself, not necessarily research in fiber per se. What are the different techniques which you can do in optical domain, which will enhance the bandwidth of your communication backbone, which is the optical fiber, right? So optical fiber is the backbone. Wireless and everything is going to be, on the peripheral side. The last mile, whatever you're talking about, accessibility, that is going to come from other mechanism. Could be wireless, could be microwave. But whenever we require a large bandwidth, right, that's where the optical fiber is inevitable. You have to use optical fiber. So all those trans-Atlantic, trans-Pacific links which connect different continents and different countries, they have to be optical fiber links because they are the only ones which is going to carry that kind of huge traffic which we are really looking for. That's where the research is. So country also needs this research because India is still growing in the requirement of communication and the data transfer and so on. Right? So this field is going to remain active for at least for a decade or so, right? And we don't know after that what happens because very difficult to predict technology, what will come after a decade. Right? But it has very great importance even for India, at this point of time.
It's really been great on your decoding of science to the very fundamentals in your research field. Since you have worked at the crucial positions and in India's few finest institutions, how do you see the current scenario of the country in a general sense? We are posing this question to you as an academician rather than an administrator, if it's possible to segregate that.
Yeah. So firstly, you're the academician. When I look at, we have to become more quality conscious, and I have been saying it very categorically. Even the graduate which we are producing, the employers say that the graduates are not employable. Okay, and many times we decode that wrongly, saying that the students don't know the advanced subject, that's why they are unemployable. That's what the decoding normally industry does. I think that's a wrong decoding. The students are unemployable because their foundation is weak. Okay, if the foundation is weak, you cannot build on the advanced subject. So what is happening at this point of time is we are undermining the importance of the foundation. Every student wants to learn artificial intelligence. Every student wants to do advanced courses, but he doesn't want to do the fundamental course. And advanced course, when you do it, advanced course lifetime is very short. The time duration, when you look at technology today, typically what is the lifetime? 5 years, 6 years. After that, technology completely changes. So if you focus on that, you will become obsolete in 5 years. What will not become obsolete? The foundation. The semiconductor physics will not become obsolete. The electromagnetic wave will never become obsolete. So this foundation which is there, if that is quality is built into that, the graduate students will be able to adapt to new technology and new science in a much more quicker fashion. So bigger problem at this point of time is we are producing in large number, but in that process we are compromising our quality. I think everybody has to become quality conscious, and I would rather say this: students should become more quality conscious, not degree centric. Well, ultimately the degree is simply going to make you stand in front of somebody, but after that, how do you perform? That piece of paper will not do. You have to do yourself. right? And that will depend upon how deep your understanding of the subject or knowledge is. So the quality consciousness, which is getting little low backseat, I think it has to be brought into the academy. There is no point in saying everybody got 99%. Somebody got 70%, but if he is worth 70%, it is much better than having somebody 99% is not even worth 50%. So this is one of my observations, that our quality in our overall thing is really getting compromised in the name of volume which we want to produce. That is one. Second thing which is important is we have to now do science or even engineering which has a more practical local relevance. A lot of science is done which is very well publishable, that publish in international journals, people get recognition and so on. Question is, how much of that science or research finally got useful for our own society? Many times even the research is done for some problem which is not related to India, maybe related to some other country. Would it have a direct impact on India? We should think about it. So we should start doing a research much more focused way, which is in quality it is global standard, but it should have a local relevance so that it can solve more and more your problem. Right? So this comes from administration also, it comes from scientific temperament also, it comes from the policies also, but it comes from the students also. So students also, I always, when I was in IIT Delhi, I had done some experiment. All students, in their engineering first year, they do this what is called NSS, social service. So in that they are supposed to do something which is socially relevant. My concept to them was, why don't you go to nearby villages or towns, identify some problem which you think there in society, and for which you think there is a solution, technical solution. You may not know the solution. There could be a technical solution. But identify the problem in first year. Remaining 4 years of your program, whenever you do the courses and subjects, keep relating to that material to that problem. Can I control this concept? Can I apply there? Can I solve this problem? You will do better relation with the societal needs and problems, even during your curriculum. And by the end of your curriculum, maybe you will be already having many more ideas because you have already started relating your concept to the real life problem. If that kind of approach is inculcated in the minds of the students, right, you will see that they will be better prepared to address the more societal issues. They will become more entrepreneurs, and that research will be much more meaningful, useful, for the development of the country as a whole. So that's what I feel should happen at this point of time.
We do understand that our nation is in an extremely unique position in the world currently with a large youth population and extremely bright people. What have been your personal learnings from the way we have been evolving in the educational system, and how can we do better at it? We constantly, get compared to the United States or perhaps European nations in this field. But most often, what happens is these opinions are not able to make an educated gauging of our standing as a nation, financially, demographically, and scientifically as well. Do you think there could be a better way to tackle this situation, in a better way to use our young brains?
Yes. So I think the core of the whole thing is the quality of education which is imparted in our country. I'm not blaming, but I'm saying if you really go and talk by and large to the student, what they want to get from their academic program? Their answer will be a job at the end of my program. That's what the answer will be: a degree and a job. Employability seems to be the only concern and issue, rather than making a solid understanding of something and contributing in a bigger scale. So our country, when we are saying that how we are evolving, I think we are creating too much on volume at this point of time, Volume is required in the country, there is no doubt about it. But while creating the volume, we also should not compromise on the quality of education. And that's what I think has to be repeatedly said. The faculty should be of quality. The student should be serious with the quality, in the quality. And there is no point in simply boasting that we produce 10 lakh engineers every year. You ask a question, what these 10 lakh engineers could do. 10 lakh engineers, when you put it, it is almost the entire population of Netherlands. No? So when I was telling somebody, one of my friend in Europe, that for JEE about 10 lakh, 1 million students appear every year. He said, oh my God, entire Netherlands is writing examination, which is true. So question is, do we have this technological impact in same proportion? And the answer probably is not very positive. And the reason is because the quality is not really up to that point.
Moving lastly and again to a personal bit, there are quite a number of creative pursuits that you indulge in, as be it playing the sitar, painting, or even poetry, or even just randomly walking, and spending time with the nature. Do you still practice these things? And perhaps I'd like to ask here one more thing, that has the way you look at the world and physics and your field of work in general changed in some substantial way that you can put a finger at, if possible, because of this creative pursuit that you have had?
It certainly does. So again, as far as the music is concerned, it so happened that I started learning sitar when I was doing my engineering in Gwalior. Again, probably it comes more like a culture of that town, that being a city of Tansen, there is a culture that people do have some inclination towards classical music. So when I was doing my engineering, which was a 5-year program that time, I got into the music college also in the evening, which is again a 5-year degree program. And I did my bachelor's of music degree along with my engineering degree, in Sitar. But then I found, that the music gives you a peace of mind at a different level. And it so happened that even after all my research and other activities, I never left sitar. I still play. So, and many times people used to ask me, do you find time to do it? And I said, I find time to play sitar only. Other things I do because I have to do it. But, but given a choice, I would like to play sitar much more. But the thing is, even if you play or listen to the music, even for half an hour, 45 minutes, I think your complete day is changed. You get a peace of mind. Even if then after that other problems come, you will be able to handle them because that particular raga in morning would have set your mind cool. Other things, of course, the poetry. When I was a student, I had a liking to write something. Again, it comes because of your social rebellion attitude. Of the things which you don't find right in around you, so you write something. I was more disturbed by these communal rights, which were there. So I could write that time around that. A lot of inequalities which are there, I could write about it. But more than that, I also like a lot of reading. And reading, not fictions really, the reading of from various thought leaders, which are there. So right from Mahatma Gandhi to other people, because reading directly puts you in contact with those people. You have heard about them, but you never talk to them. If you read what they wrote, you directly get in contact with them. You see their thinking process. So I was reading recently the book on Maxwell, the life of Maxwell. Maxwell has a personality which always helped me so much. That a single person, how can somebody do so much of work? So Maxwell put his hand in every possible thing. He worked in thermodynamics, he worked in electromagnetics. Maxwell's equations are known anyway. But he has many more distributions, Boltzmann, Maxwellian distribution, and various things which are there in Maxwell. So when I was reading his life, I found that he used to take a problem, try the problem for a year or two. If it doesn't get solved, he used to leave the problem there. He will go to his house, in the village, and spend 1 or 2 years in building his house. Don't do science, I after 2 years come back and look at another problem which looks much more interesting. Start working on that. Everything interconnected. No, you could build your house also. At the same time, you can solve Maxwell's equation also. You can write a Boltzmann distribution also. You know, so there is no bound on you. If you really like something, if you are interested in that, you can really produce wonders after that.
This was Zeroing In with Dr. Raghunath Kashinath Shevgaonkar. We extend our sincere gratitude to Dr. Shevgaonkar for sharing his inspiring stories and such inquisitive ideas from his elaborate experience, along with Prajwal Patnaik for collaborating on this episode on behalf of the Zeroing In Season 2 team, which includes Arun S., Kandan Narayanan, Priti Raj, Murala Aman Naveen, Sean Ethan Chaudhary Fancher, and I am Shreya Mishra. Thank you for listening to this episode. Zeroing In is a non-profit initiative brought to you in collaboration with the Alumni Association of the Indian Institute of Space Science and Technology, Thiruvananthapuram. If you have any suggestions, you can write to us on zeroinginpodcast@gmail.com or contact and follow us on our Instagram and Facebook handle @zeroinginpodcast.